This is the start of video 2 on Intro to IMFs. We're going to talk about the types of IMFs. We already reviewed how to draw our covalent compounds. Now we're going to look at what are the different types of intermolecular forces that we are going to find. So those intermolecular forces, they are determined by what our individual molecules look like. And because then we're going to look at, well, how does a CH4 molecule, how is that going to interact with other CH4 molecules? Same thing with these ones here. So with these different types, we're going to go through those different types and look at how we can classify types of IMFs. Our first type of IMF is called London dispersion forces. And this is a type of van der Waals force, which is a weak electrostatic force that attracts neutral molecules to one another. And so this is our weakest of our IMFs, and it occurs in nonpolar molecules. So our electrons are being shared equally in that molecule as a whole with that. And so as we are looking at CH4, which we drew up here and we determined that that was nonpolar, we also determined that with our SO3. CH4 that has London dispersion IMFs. So does CO2, because again, we have no lone pairs on the central atom, and any unequal sharing on the sides is going to cancel out. And same thing with our hydrogen. This is supposed to say that H2. Anything that's diatomic is going to be a nonpolar covalent molecule because it is sharing equally with itself. Hydrogen and hydrogen have those same electronegativity. So why is this the weakest force between attracting neutral molecules to one another? Well, when we have these nonpolar molecules, those electrons are being shared in our bonds. We have, here's an electron being shared here. And while we can say they share equally, those electrons are shared equally, but they're always moving. So maybe hydrogen is hogging it a little bit, and then it's moving back to carbon. And so the partial charges that we get are going to be temporary. And so we might have, here's my molecule. Let's say that this is a hydrogen molecule. We draw this and we say, okay, it's going to share equally, but what's really happening is that maybe at one instance, those two are closer to one of my hydrogens, and then in the next instance, it's closer to my other hydrogen. And so that sharing is equal, but it keeps moving back and forth, and so we get temporary partial charges that are always changing. And so once those move to the other side, it's going to impact how that hydrogen molecule is interacting with other hydrogen molecules around it. So if we have temporary partial charges, that's going to lead to London dispersion IMFs, London dispersion forces. If we get now some permanent partial charges, that's where we get another van der Waals force, which is a weak electrostatic force, but this is going to be a little bit stronger. And now if we have polar molecules, so polar covalent molecules, our electrons are going to be shared unequally, which means that that more electronegative atom is going to create permanent partial charges. So that unequal sharing in the molecule means that dipoles forming permanent partial charges in the molecule. So we've got hydrogen and chlorine. This is not a symmetric molecule between those two. Chlorine is more electronegative because it's closer to the top left. So it's going to have that partial negative. Hydrogen's going to have that partial positive. So while there are these electrons being shared, those electrons are going to be closer to chlorine, even though they're not getting completely transferred to chlorine. Looking at our SO2, sulfur and oxygen, well, oxygen is more electronegative. And so oxygen is going to have those partial negative charges. Sulfur is going to have that permanent partial positive because in this sharing, even though they're sharing, oxygen is going to hold those closer like that. Same thing if we look at this HCN. When we look hydrogen, carbon, and nitrogen, our nitrogen is most electronegative. And so that nitrogen is going to be hogging the sharing of those molecules, and that would have that partial negative on that end, and overall our hydrogen would have that partial positive. So dipole-dipole forces, are going to occur in those polar covalent molecules where we get permanent partial charges occurring. Because then again, kind of like we have down here, that negative chlorine partial charge is going to attract the positive hydrogen partial charge from another atom or molecule, excuse me. All right, so these were both of our covalents. So if we are going to determine if each of the following has London dispersion or dipole-dipole, well, both of these are going to be covalent, so then we just need to look at that polarity. So F2, if we look at, well, how is fluorine going to share with another fluorine? We can draw that. Anything that is diatomic is going to end up being nonpolar because it's going to share equally with itself, which means if that is nonpolar, there are no permanent dipoles forming. And so this one is going to be London dispersion because that is a nonpolar molecule. CH4, we've drawn that one a couple of times. We've got carbon surrounded by those 4 hydrogens. And we also have determined before that that is nonpolar, meaning that London dispersion is going to be the IMF. H2O, I don't think we've drawn this one yet. Oxygen goes in the middle, hydrogen on each side, make everyone happy. Oxygen is happy with 8, so we need 2 lone pairs. Each hydrogen is happy with 2, so those are happy there. And so then now we have this covalent molecule. I'm going to determine that polarity. Well, I have lone pairs on my central atom, and those lone pairs indicate that this is a polar molecule, which means that this is going to have dipole-dipole IMFs. If we were to look at that, oxygen is more electronegative, so it would have that partial negative. Those hydrogens would have those partial positives. CH3Cl, if we have something that is made up of multiple of those things, carbon needs 4 electrons, so that's going to go in the middle. And then we have hydrogen on 3 sides. I'm going to put chlorine on one of the sides, making everyone happy. Carbon is happy with 8, 2, 4, 6, 8. Each hydrogen is happy with 2. My chlorine then needs its 3 lone pairs. So I've got that drawn. Again, checking, there's nowhere for me to form any double bonds, so I can't, I don't need to do that here. And then looking at, well, there's no lone pairs on my central atom, but this is not symmetric. So this will be polar, which means it is going to have dipole-dipole IMFs. If we look, chlorine is more electronegative than carbon, so it's going to have that partial negative, and so that dipole would point towards our chlorine. pH3, phosphorus goes in the middle, 3 hydrogens, a lone pair on phosphorus to make it happy. We have nowhere that a double bond could go, so I don't need to do any editing. I can make sure that I have the 8 I need from my periodic table. Phosphorus has 5, each hydrogen has 3. And then this has a lone pair on that central atom. And so if there's a lone pair, that means this is polar, so this would have dipole-dipole IMFs. And again, phosphorus is, I believe, more electronegative, so that would go towards phosphorus. Usually we can use our trends to determine electronegativity. If there's something specific, then you can just use those trends to determine that you aren't going to have access to the electronegativity values that you might need. All right, so we've got London dispersion is if we have covalent compounds that are nonpolar. Dipole-dipole is covalent compounds that are polar. And within dipole-dipole, we actually have a special or a stronger type of dipole-dipole, which is called hydrogen bonding. And this is present in some polar molecules. Again, the electrons are shared unequally. And this is a result of the high electronegativity of nitrogen, oxygen, and fluorine, bonded with lower electronegativity hydrogen. So if we have dipole-dipole and there is at least one hydrogen-oxygen, hydrogen-nitrogen, or hydrogen-fluorine bond, then more specifically than dipole-dipole, that is going to be called hydrogen bonding. It's a misleading name because it's not really a bond. It is a force, an IMF. And so when we see NH3, because we have that large difference between nitrogen and hydrogen and their electronegativities, our nitrogen is a lot more electronegative than those hydrogens. We are going to have that strong difference in sharing, and so that hydrogen bond is going to be present. So when we see any of these hydrogen, nitrogen within our molecule, that means that that nitrogen is going to interact with hydrogens on other molecules with having a very strong attractive force. If we look at H2O, H2O also has hydrogen bonding. When we did our intro activity, you should have seen that water, H2O, more droplets would fit on the penny than of our other chemicals, and that is because of that strong hydrogen bonding. So the positive pole, the partial positive of the water molecule, is attracted to the negative pole, the partial negative of the other, and that is forming that hydrogen bond. Depending on the compound and how many lone pairs are on the most electronegative atom, a molecule may have multiple sites for hydrogen bonding. And so this is hydrogen bonding. Nitrogen only has one spot for that hydrogen bond to occur, which is that IMF. And so that is the site of hydrogen bonding that nitrogen can only attract one hydrogen on a different atom. But if we look at our hydrogens and our oxygens, this oxygen could attract two hydrogen bonds with hydrogens from other atoms. So one there, and it could attract one here, but it would have to be from another H2O. And so we do need to also then determine, well, how many places could my hydrogen and my oxygen be attracted? So this one has two sites of hydrogen bonding. This one only has one. And so depending on the compound and how many lone pairs are on the most electronegative atom, a molecule may have multiple sites for hydrogen bonding. And so again, we have an H2O because each of those oxygens has a lone pair. That means that there are two sites for hydrogen bonding on each of those oxygens. So, which of the following contain hydrogen bonds and how many potential sites for hydrogen bonding are there on each? So we need to, if it contains hydrogen bonds, we need to make sure that it is polar. But then, in addition to being polar, we're going to look for, is there a hydrogen-oxygen bond? Is there a hydrogen-nitrogen bond? And a hydrogen-fluorine bond. So we're looking specifically for one of these three in a polar molecule. H2O, oxygen in the middle. We have those hydrogens, making everyone happy, and oxygen's happy with two. This is polar because of the lone pairs. And I have HO bonds, which means that this is a hydrogen bonding IMF. So because of those lone pairs not being polar, that means that it is dipole-dipole, but more specifically, it is hydrogen bonding. How many sites for hydrogen bonding? Well, my oxygen is more electronegative. And so on that electronegative oxygen, I have two lone pairs, which means that I have two sites where those could bond to hydrogens in other molecules. Next one is HCl, hydrogen and chlorine, making each of those happy. Hydrogen is happy with 2, chlorine's happy with 8. So now I have this molecule, it's covalent, it is polar because it is not symmetric. So we know that it is at least dipole-dipole, IMFs. Then we need to look, does it have hydrogen oxygen, hydrogen nitrogen, and hydrogen fluoride or hydrogen fluorine? No, it does not. And so this one has no hydrogen bonding. The strongest IMF is that dipole-dipole. NH3, I think we've drawn this one before, nitrogen in the middle, hydrogens on each side, and a lone pair to make nitrogen happy. So this one is polar because of the lone pairs, which means we have at least dipole-dipole IMFs, but we then need to look at, do we have one of these three? Well, we have those nitrogen-hydrogen bonds, which then means that the strongest IMF is hydrogen bonding. And how many sites of hydrogen bonding are there? Well, we need to look at how many lone pairs are on our central atom. Nitrogen has, because it has one lone pair, it is going to have one site for hydrogen bonding. One place that our nitrogen, which is going to have that partial negative, is going to be attracted to those partial positive hydrogens from a different molecule. All right, so the covalent ones are a little bit trickier because we need to look at polarity. Once we get beyond that, metallic and ionic are very simple because they fit kind of into one category. Metallic bonding, again, this is misleading because it is an IMF, metallic bonding. It occurs if you only have metals, recognizable from the formula. So if you only have metals, we've called those metallic before. And the electrons of our metal atoms are shared with all of those atoms in the sample, all the electrons are shared with all the other atoms in the sample. So those delocalized electrons, and this explains why metals bend but remain strong. And so metallic bonding, or metallic IMF, so a metal between a metal, it's not, we talked about it when we were talking about our bonding notes, but really we should be talking about it only here when we're talking about those intermolecular forces, not intramolecular forces, because a iron atom is really has an IMF with other irons. It's not actually within an iron molecule. So anything that is metallic is going to have metallic bonding IMF. Next, ionic bonding, misleading again, not really a bond, but it is that strong attraction, that force. And if we have an ionic compound with a metal and a nonmetal, then ionic bonding is the IMF, so we can recognize it from that formula. The crystals are very hard, but shatter because, again, they might break apart in certain spots, but they're not all going to break apart from one another. So if something is an ionic compound, its IMF is ionic bonding. Our last one, and this is the strongest, so we've been going from weakest to strongest, is covalent network solids. And these are recognizable from the formula, and it's where multiple connections are made between each atom, which contribute to strength. And so we see this with carbon. Carbon has 4 valence electrons, which means carbon is going to do a lot of sharing with other carbons. And that's how we get all that sharing. We kind of get that like human knot or electron knot of sharing. The electrons aren't delocalized. They're going to keep their electrons and share them between each other. And so things that have that ability to share a lot, they are covalent, but because of that multiple sharing on all sides, they're not going to form individual molecules. That's our covalent network solids. So carbon by itself is a covalent network solid. Silicon by itself, which is right under carbon on the periodic table, so it also has 4 valence electrons. And silicone compounds, so silicone and anything else, are going to also be covalent network solids. Why would this not include compounds made of silicone and hydrogen? Well, silicone, if it has 4 valence electrons, it's going to want to bond with 4 things. So by bonding with hydrogen, it is not going to have that kind of same structure that we would want. And so that's why it's not going to be that carbon and silicone compound. We would have to have actually 4 hydrogens around it. And those hydrogens are not going to keep sharing because those hydrogens are happy with just 2. They're not going to share on any other sides. And then the one compound that has carbon in it, tungsten, it has the symbol of W. Tungsten carbide is the one carbon compound that has covalent network solid as its IMF. These ones, you do just have to kind of know that it is carbon, silicone compounds, and tungsten carbide. Those are the kind of three specifically, and then that one group that has covalent network solid as their IMFs. All right, so we went through these ranking by strength. We went from nonpolar to polar, and then lots of sharing, and to so polar they can't even share, and covalent network solids. So our weakest is those London dispersion, to our strongest, which is the covalent network solid.